Hello, young scholars. Here we are once again, preparing for a test, this time on Newton's laws. Our first problem from the free response section involves a mass supported by two cables, um, equally it says, so each one will have the same tension force, which we can represent by the same variable, T. Um, of course, we seek to find that spot where the three forces meet up, and that is the knot. And if we analyze the forces, we can see that in the x direction, there are two forces, one positive and one negative. But in the y direction, there are three forces, two positives and one negative. Let's take a look at those forces. If we break them up into their components, in the x direction, we have Tx running this way. Let's label that Tx. We have Ty running this way. Oops. Let's label that Ty. And then we have the same situation happening over here, Tx and Ty. So from the perspective of the knot in the y direction, and we choose y because it has the known tension force down here, we can say F net equals ma. But since nothing's moving, we can say that the acceleration is 0. And now let's describe our three forces in the y direction. We have this Ty, which is positive. And let's see, what is that T? Well, it's going to be T sine of this angle. But that angle must be 45 degrees. Since this is a 90-degree angle, the problem says that. And this is the horizontal here. So this must be 45, 90, and another 45. So we can say T sine 45 going up plus another T sine 45 going up. So we have two T sines 45 going up. So I'm going to just write 2 T sine 45. I could write T sine 45 plus T sine 45, but let's just write it as 2 T sine 45. And then we have a negative force going down. How big is that tension force? Well, it's got to be exactly big enough to support this mass. And that mass has a gravity force of mg, so that means the tension force pulling down must equal mg. And now we're prepared to solve for t. We can move the mg to the other side of the equation. And it will become positive. And then divide both sides by sine 45. Sine 45. And that should describe this t and equivalently that t. Okay, let's move on to the next problem. This one's a little different. Here we have a puck going around in a circle attached to a string. The string goes through a hole and is pulled downward by this weight right here. So this weight has a tension force on it. That tension force continues all the way to this puck here, and this tension force provides a centripetal force toward the center of the circle. This is a frictionless surface, so we don't have to worry about any friction up here. And the goal on this problem is to find the, let's see, it is to find the mass of the puck. So we are after this, the unknown here is the mass of this puck. So let's begin by writing F net equals ma. That seems like a good place to start. F net equals ma. And since we're moving in a circle, we can replace our a with v squared over r. Now the m here is the m of the thing that's going in the circle. So that's the mass of the puck up here, and that is indeed the mass that we're after. Okay. Now let's take a look at the left side of the equation. How many forces guide this thing in a circular path? Just one, just the tension force. So we can say Ft. Okay. How big is that tension force? That tension force is the same throughout the whole string, so that tension force must be exactly big enough to support this 800 gram mass so it neither accelerates up nor down. So that must equal the mg of this mass. So I'm going to say that this tension force is, let's call this m2 maybe. I'm going to say that this tension force is equal to m2 times g. Let's take a look at our picture here. Do we know m2? Yes, it's given. Do we know g? Yep. Do we know v? Yep, it's given. Do we know r? Yep, it's given. So we simply have to solve for m, and we should be okay. Next problem. Here we have a wet sock and a washing machine that is spinning around in a circle. And the first part of this question asks us to calculate the acceleration of that sock. Well, since it's going in a circle, the best way to calculate acceleration is v squared over r. Do we know v? Yes, it's given up here, 4 meters per second. You have to square that. Do we know r? Well, we can get it. The diameter is a half a meter. The diameter is all the way across. The radius is half of a diameter. So half of 0.5 is 0.25. And there's our acceleration. Part B is this centripetal or centrifugal. I'll let you decide that. And part C, we're going to try to find the mass of the sock. We're told that the net force on the sock, the net force, is equal to 3 newtons. Well, let's take a look at the forces acting on the sock. What is the net force? We've got a normal force going toward the center. That's our centripetal force. We've got a friction force going up, a static friction force, and a gravity force going down. These two forces must cancel because there's no upward or downward acceleration. So the net force is the normal force. So that is our normal force, which is also our centripetal force. So if we say F equals ma, and our A we have from part 1, so we know that, check, whatever that v squared over r is. Our net force here, based on our diagram, is simply our normal force, which is 3 newtons. That's our normal force. And therefore we can solve for m because we know everything else in the equation. Let's move on to the next one. This is a problem we've seen a few times before. I break it down into little parts for you. Part A is, which way will the system accelerate, right or left? I think you can see that it must accelerate that away, to the right. Part B, let's figure out the gravity force on each one. This mg is 9.8 newtons. This mg is 29.4 newtons. That's just m times g. Part C is what's the net force on the system. By the system, we're talking about the whole thing. So let's see if we can figure it out. Remember that when we see a pulley, we straighten it out. So we've got a force of 29.4 going this way. We've got that's newtons. We've got a tension force going that way, unknown. And when we swing this guy out, We've got a force of 9.8 newtons going that way, and we have a tension force this way. These two tension forces, of course, are the same. If we want to look at the force on the net force on the whole system, these two tension forces will cancel, and we have a positive 29.4, a negative 9.8. The net force here will be the combination of those two, paying attention to plus and minuses, 29.4, negative 9.8, and together that comes out to 19.6 newtons to the right, positive. Okay, and that must equal the mass times the acceleration of the system. Of course, the mass of the system must be both of those together, 4 kilograms. So now we can figure out the acceleration of the system. Here's the net force of the system. Divide both sides by 4, and we have the acceleration. And let's see, what's 19.6 divided by 4? It looks like the acceleration must equal 4.9 in this example. And the last part of the question, part E, asks us to find the tension force. Now, the tension force is internal to the whole system, so we need to choose a smaller system. Let's see, maybe this would be a good system. Either one is good. If I choose that as my system, I can say that F net equals ma. Always wise. The mass of this system, 3. The acceleration of this system, 4.9. How many forces are involved? 2. 29.4 positive and T negative. Solve for T. Next question, also number 45. Here we've got a force of 60 newtons accelerating a 5 kilogram block, 5 kilogram block at 6 meters per second squared along a horizontal surface. Of course, there's going to be a gravity force and a normal force, and presumably there's some kind of a friction force. So let's try writing F net equals ma for this situation. I think there's no doubt about what the m is. I think there's no doubt about what the a is. There are 2 forces involved in the x direction, the direction of the acceleration, a positive 60 and a negative kinetic friction force. So you can solve for the kinetic friction force there. And then part B is, what's the coefficient of friction? Well, once you have that number, you know that it's also equal to mu k times the normal force. But from our diagram, we can see that the normal force is equal to mg. So we can solve for mu k because we will know the normal force and the kinetic friction force that we solve for up here. So mu k is easily obtained. Okay, let's move on to question number 4646. This one has many parts. Let's start with part A. What is the net force on the truck? Well, the statement is originally that it does not move. Velocity equals 0. Not moving. So that means acceleration equals 0. What is the net force when the acceleration equals 0? I'll let you decide that. Part B. What is the normal force on the truck from the ground? Well, here it is. There's the normal force on the truck from the ground. It must be equivalent to the gravity force. These two forces must be equal, otherwise you have that weird floating up into the air or burrowing down into the ground situation. So that normal force equals mg, the mg of the truck. Part C, what is the frictional force on the truck? Well, in the x direction, we only have two forces. We've got the 1500 Newton pushing force to the right, and then we've got an unknown friction force to the left, but again, it's not yet moving, so acceleration is 0, and so solve for your friction force. There you have it. Part D, now we got a new situation. Now we're going to up our force from 1500 to 2500 newtons. And it says it just gets the truck to move. That means we're on the verge of slipping, on the verge of movement. So we can go to our static friction equation. Actually, our static friction inequality. And since we're on the verge of moving, the equals part of that becomes active. It's in play. Because this represents, remember, the maximum static friction you can have. But if you're on the verge of moving, you have just reached that maximum. So 2500 newtons just gets the truck to move. What's the mu s? Well, let's write F net equals ma. Never a bad idea. Verge of slipping, we still don't have any motion yet. It's just about to happen, so no acceleration. We've got 2500 newtons for our positive force and a static friction force trying to hold us back, but that is going to be equal to mu s times the normal force, which we have previously calculated. So from that you can get mu s, the coefficient of static friction. And lastly, what will be the acceleration observed with a 3000 Newton push? So now we're changing things again. Now we're up to 3000 newtons. We're making the assumption that the coefficient of friction, whatever you calculated here, is also equal to the kinetic coefficient of friction. So once again, in blue, maybe we'll erase a little area here. In blue, we can write Newton's second law once again, F net equals ma. But now we will have some acceleration. Our mass is 2,000 kilograms, the mass of the truck. Our net force is 3,000 in the positive direction, and now we've got some kinetic friction in the negative direction. That will equal mu k times the normal force. It's the same normal force, that hasn't changed, and the mu k we should have from our calculation of mu s. So if we look at our equation here, we've got our pushing force, we've got a known mu k from part B, we've got the mass, we've got an unknown acceleration, that's what we're solving for, that's our unknown, that's what we want, and we know the normal force from part B. So we have everything we need to solve for the acceleration. Okay, I think we are on to our last problem from the free response section. This is a doozy. Let's take a look. So here we have a 3 kilogram block, 3 kilograms, and it is starting at the top of a ramp, and it says that the ramp has a length, that's referring to from here to here, of 1.0 meters. And it's got a height of 1/3 of a meter. Well, a little bit less than 1/3, 0.3 meters from top to bottom. Before we get too excited here, we probably should spend a moment calculating that angle. because that's going to be very important when we look at the forces up here. So let's see, what is the trig function that relates this angle, the opposite side, and the hypotenuse? I do believe that's sine. Sine of that angle should equal opposite over hypotenuse. That's the definition of sine. But in this case, our opposite is equal to 0.3. Our hypotenuse is equal to 1. So if we inverse sine both sides, we get that the angle is equal to inverse sine of 0.3 over 1. Great. That's going to come in handy. Now let's take a look at a force diagram here, because clearly we're going to have to understand what's going on with the forces. So we naturally have a gravity force going straight down. Redraw that. Okay. We've got a possible friction force going back that way. And we've got a normal force coming straight off the ramp like that. And that looks pretty good. And we need to choose a coordinate system like always. And since the acceleration is going to be down the ramp, we want to have a coordinate system that is consistent with that positive direction. So anything pointing down the ramp we shall call positive. Anything that is perpendicular to the ramp will have no acceleration. And anything that's going up the ramp we'll call negative. If we look at our forces here, we can see that the mg force is the one that needs attention. It's not pointing in the x or the y direction. So let's see here. Maybe we should go back to the problem itself. Part A asks us to figure out the acceleration. That can be figured out with our old equations of motion, because we know a distance traveled, d equals 1 meter. We know a final velocity of 1.5 meters per second. So meters per second. So I think our equation number 4, v final squared equals v initial squared, which is 0, plus 2 times acceleration times distance traveled seems like a good place to begin, and then we can solve for the acceleration. Once we have that, we're prepared to figure out B, the net force. Since the net force automatically equals ma, we will have A, and m is given. Part C asks us to figure out the gravity force. Enough said. Part D asks us to figure out the component of the gravity force along the ramp. What are we talking about here? We're talking about, let's see, here's the gravity force. Here are the two components of the gravity force, one of them on the y-axis going that way negatively, and one on the x-axis going in that direction. If we're asking for the component of the gravity force along the ramp, we are talking about this force right here, and that force should equal mg times the sine of our same angle theta that we have previously calculated. So question D is looking for mg sine theta. For the next thing, we're trying to figure out the friction force, E, the friction force. And the friction force is showing up right here. So how do we get the friction force? Well, maybe now it's time to write F net equals ma. Let's switch colors. have net equals MA. Do we know M? Yes. Do we know A? Yes. That was we got from part A. Let's describe the net force in the x direction. We've got this force pointing in the positive direction, mg sine theta, our answer for D. And working in the negative direction, we have our friction force. So let's take a look at this equation. We know M, we know A, we know M, we know G, we know sine theta, we want the friction force. Next. Can we fit this all on one page? Maybe. Part F. Find the normal force. Many of you are making a mistake of saying that the normal force equals the gravity force. Only true when you're on a flat surface. Not true on a tilted surface. Let's take a look at our picture here. This is the normal force up here, pointing upward, the normal force. In the y direction, the normal force points positive, and the only other force in the y direction is this one. The normal force must be balanced not by mg, but by this, mg cos theta. Hope you guys got that. Finally, we're going to figure out our coefficient of friction, part G. We know that the kinetic friction is equal to mu kinetic times the normal force. Do we know the normal force? Yes, we just calculated it in part F. Do we know the friction? Yes, we calculated it in part E. So we know both of those, and we should get a good value, hopefully between 0 and 1, for our kinetic coefficient of friction. This concludes your hints for the Newton's Law test coming soon. Good luck, everybody. I wish you the best. And oh, if you want a tiny bit of extra credit for being such a scholar and paying attention to this video, let's see what you need to do for that. You need to go to the truck, wherever that went to. Truck, truck, truck. There it is. And on the truck, you need to draw a little headlight with some light coming out of it. And if you do that, I will know that you've watched the video, and I will credit you for your scholarly work. Thanks for watching, and good luck on the test.